Hi everyone. Our lesson will focus on matrix representation of images and will explain the connection between linear algebra and image processing, specifically in terms of resizing and rotating an image. However, before we go into that, it's important to understand how images can be represented as matrices within a 2D space. At the most basic level, an image is a collection of pixels. Each pixel has a color or intensity value, and the entire image can be represented as an array or matrix where each element corresponds with the pixel's value. In linear algebra terms, this means that an image is represented as a matrix. For grayscale images, each pixel has one value representing its intensity or brightness, usually ranging from 0 to 255, 0 corresponding with black and 255 corresponding with white. Let's say the image is m by n pixels, m representing rows and height, and n representing columns and width. This image can be represented by an m by n matrix where each entry is a number representing the intensity of the pixel at that location. For example, the matrix you see on your screen is an example of a grayscale image, where each element represents the intensity of a pixel. However, for color images, the RGB color model is typically used, where each pixel has three values corresponding to the intensities of red, green, and blue. The picture is then represented as a 3D array, where the first two dimensions represent the height and width, and the third dimension corresponds to the three color channels. For example, a 2 by 2 color image with RGB values can be represented as the three matrices you see on your screen. Each of these matrices corresponds to a specific color channel of the image. Combining the three gives us a full image. So now that we have and understand an image as a matrix, linear algebra gives us the tools to manipulate and process these images in various ways. Matrix operations and linear transformations, for example, allow us to alter these images. Some changes we can make to an image using matrix transformations are scaling and resizing, rotating, translations, etc. However, in this lesson, we will only focus on image scaling and rotating.
Now that we've seen how images can be represented as matrices and how they can be scaled using linear algebra, let's look at another fundamental image transformation, rotation. So in this chapter, you'll learn how to rotate an image using matrix multiplication. So just like resizing, rotating an image also relies on matrix operations, namely multiplication, as I stated earlier. So this is an important function because rotation can be used in graphics, animation, and even computer vision applications like facial recognition. And once again, to rotate an image, we use a rotation matrix, which we're calling r theta, which alters the pixel coordinates. So let's break this all down mathematically. How do we rotate an image? Once again, as I mentioned earlier, we're going to be multiplying the original coordinate vector of our pixels by the rotation matrix r theta, which can be represented as cosine theta, negative sine theta, cosine theta. So when rotating an image, each pixel's coordinates change according to the transformation matrix. And this matrix multiplies each pixel's coordinate vector. So given an example, just amplifying what we have written on the bottom right of the previous slide. X and Y are our original pixel position. And when we're multiplying our pixel position, our coordinate vectors, or coordinate matrices by the rotation matrix, we need to keep in mind the rules for multiplication of matrix multiplication. So making sure the columns of the initial vector matches up with the rows of our new vector. I'll just restate that so we're not lost. X, Y is the original pixel position on the far right. X prime, Y prime is the new pixel position after rotation. And in our center that's being multiplied by our original pixel position, we have r theta, where theta is the rotation angle measured counterclockwise. So the same way that you'd find theta, sine theta, cosine theta of an angle given the unit circle, just traversing it that way, that's the same way we're going to really think about the angles that we're using and our values for r theta, the rotation matrix, when multiplying.
Here we have an example of a 90-degree counterclockwise rotation. In this case, for when theta equals 90 degrees, you're going to substitute its 90 degrees with the matrix here, where there's 0, -1, 1, and 0. And then what you do is you apply it to a point, and essentially here, the point 3, 2 is rotated by 90 degrees, which would essentially become -2, 3. So how does this apply to a whole image? Well, each pixel in an image has the coordinates x and y, and to rotate an entire image, the rotation matrix is applied to every single pixel. It's important to note that not all rotated coordinates will stay within the original image size. Also, some pixels may move out of bounds while others land between pixel positions. To correct this, we use interpolation, which estimates pixel values that don't land exactly on a grid point. Here we have another example where we're rotating a simple 3x3 image. Consider the following 3x3 grayscale image that's represented with this matrix. If it's rotated 90 degrees counterclockwise, the new positions of the pixel will be here, as follows. In this case, each row becomes a column in the rotated image.
R theta is a rotation matrix which allows rotating an image by any angle. Every pixel's new location is determined using matrix multiplication, and filling the grid is the interpolation which helps fill in missing pixel values in rotated images.
Now let's move on to scaling an image and transforming properties of coordinate matrices.
Each coordinate pixel can be multiplied by a scaling factor to scale an image. This process can involve multiplying an image matrix by a scalar value or a scaled version of the identity matrix. This section will address how digital representations of quantized real-world analog images are transformed and processed. The umbrella term used for referring to such activities is digital image processing, or DIP, which entails the manipulation and analysis of images using computer programs and algorithms. DIP encompasses the methods used for performing operations on image representations to accomplish a certain goal or extract information. It is a form of signal processing in which the input is an image and the output is another image or a feature present in the original image. DIP does not include image acquisition or generation of digital image representation from analog signals. Most image processing algorithms implement the following steps. Use an input method to either read or import the image, analyze, manipulate, or modify the image, and use an output method to export the processed results, which is an altered version of the image received via input. When image processing algorithms manipulate 2D image representations, they often utilize concepts from linear algebra to accomplish image transformations, because a 2D image representation can essentially be treated as a matrix. Image transformations in DIP are generally accomplished with the help of transformation matrices, which are special matrices designed to accomplish the goals of image processing through matrix algebra. The extent and complexity of matrix operations in image transformations are dependent on the type of transformation desired. This lesson will focus on relatively easy type of image transformation, referred to as image scaling. Image scaling is a widely used feature in browsers, image viewers, image editors, thumbnail image generation, and outputting of images on printers and computer screens. Image scaling entails both an enlargement and shrinking of an image. Enlarging an image is referred to as upscaling, and shrinking of an image is referred to as downscaling. In either case, no changes are being made to the original image.
In this section of the video, I will be talking about some key concepts related to image scaling, such as image size, uniform and non-uniform scaling, commonly used image scaling algorithms, the quality of a scaled image, and the representation of images as bitmaps, which is a requirement for scaling algorithms. Image scaling algorithms take an input image of size x and generate an output image of size y, which is different from size x. Image sizes x and y are expressed as the number of rows and columns of image pixels. For example, an image size of 9 by 9 implies that it has 9 rows and 9 columns of pixels. Images can be upscaled or downscaled in either a uniform or non-uniform way. In uniform scaling, both rows and columns are scaled by the same factor, but in non-uniform scaling, rows and columns are scaled by different scaling factors. Image scaling algorithms perform mathematical operations to either scale the image up or scale it down. Commonly used algorithms for image scaling include the nearest neighbor, bilinear, and bicubic interpolation. These algorithms use the information present in the pixels of an input image to generate the pixel values in the new image. These algorithms cannot add any new information or details to the target that was not present in the original image. Hence, the quality of scaled images is dependent on the quality of the original image. Scaling algorithms work exclusively with pixel values. This implies that they expect the input image to be represented as a bitmap. An image represented with the help of a bitmap is often referred to as a raster image, which is nothing more than a rectangular array of pixels in which each element of the array representing the location color can be attributed to a pixel. In this slide, I will talk about basic level transformation matrices that one can use to enlarge or shrink image sizes. Please note, when we are working with transformation matrices, we are dealing with image size and not individual pixels. To change the size of an image, we use a scaling transformation matrix, which can be expressed as follows, in which A is the scaling factor across the horizontal dimension, and B is the scaling factor across the vertical dimension of the image. For enlargements, A and B are greater than 1. If A is equal to B, then this is the case of uniform scaling. If A is not equal to B, then this is the case of non-uniform scaling. In the case of downscaling, A and B are less than 1. For example, if a 3 by 3 image needs to be uniformly scaled by a factor of 3, then the scaling transformation matrix can be expressed as follows. Similarly, if a 16 by 16 image is to be uniformly downscaled by a factor of 4, then A is going to be equal to B, which will be equal to 1/4. And the scaling transformation matrix can be expressed as follows. Using transformation matrices. The transformation matrices can be used to compute the size of the target image using this relationship, in which x1 and y1 are the dimensions of the scaled image and x and y are the dimensions of the input image, and this is the transformation matrix. Using the example of upscaling a 3 by 3 image by a factor of 3 from the previous slide, we get this relationship, in which x and y are equal to 3, and x1 and y1 are equal to 9, and we have the transformation matrix 3, 0, 0, 3. Hence, the dimensions of the upscaled image will be 9 by 9. Similarly, the size of a downscaled 16 by 16 image will be 4 by 4 if we want to shrink by a factor of 1/4. In this case, x and y would be equal to 16, and x1 and y1 would be equal to 4, and a and b would be equal to 1/4. So we would get the transformation matrix 1/4, 0, 0, 1/4. Now give it a try on your own using these examples. Thank you.